Okay, so today I want to speak about roots and root subgroups. If I have time, tomorrow maybe I come uh, I come back to a few things of the lecture of yesterday, but as you can see in the notes, some of the intermediate results are interesting in themselves. So there are some kind of rigidity results that were proved in the course of the proof of the main theorem. Okay, but I want to speak about roots. So let G be a reductive group scheme over S, and well, so assume as we saw, well, so if we take any point in S, so we saw yesterday that there exists some étal neighborhood U of S such that the GU contains maximal torus T. Okay, so actually, so we assume S is equal to U. Okay, so we assume that there exists a maximal torus which exists over S. And I just recall that this is not a very big constraint because we know that this is the case étal locally. Okay, and so since G is smooth and hence its Lie algebra is vector bundle over S. And it is endowed with the adjoint action of G itself, and in particular of the torus. And we have seen already that the T invariance in the Lie algebra, this is the Lie algebra of the torus that I will denote by a T like this. And hence, okay, so by a result that we saw about a representation of a torus, we have so that the Lie algebra is a direct sum. Ah, okay, and contains yeah. So let's further assume that the torus T is a split. So this is the diagonalizable group corresponding to some abelian group. And actually, so M is some free abelian group of some rank. And here we have all the non-zero, well, all the weight spaces corresponding to non-zero characters of M. And each GM the direct summon in G is also a vector bundle. Over S. And by the classical theory, over each geometric fiber, we get that each GM is either 0 or one-dimensional. Because we know that in each geometric fibers, the root spaces of our Lie algebra, so the root spaces are one-dimensional. Okay, so we have this, and well, I put vector bundles in quotes because S need not be connected. So the rank of the vector bundle can depend on the connected components. So here also it's I put some quotes here. And now we define okay, and also so recall that the set of the morphism of S groups from our torus T to the multiplicative group. So this is a set of locally constant functions from S to M. Okay, so if S is connected to give a morphism from T to GM is just giving an element of M, and if S is disconnected, it may depend on the, okay. And so we have the following definition. So which is from SGA 3, 1932 and 36. So given the pair GT as before, that is G reductive and T a split maximal torus. Okay, so and so by definition, so this is a section over S of the constant group scheme MS. Okay, so so what we call a root of GT is locally constant function alpha from S to M minus 0 such that for any point S the fiber okay, so the fiber. So we look we consider the weight space corresponding to the element M, which is alpha of S, and so the fiber of this bundle at S is non-zero, hence one-dimensional. And okay. And let us remark that in this case, setting well, if I call M this alpha of S, then GM is a line bundle of constant rank 1 on a neighborhood of S. Okay, so, and secondly, we say, so that's the definition of a root. And we say a set of such, a set R of such roots is called a root system. The root system of the pair GT if one has, if G is, well, so the direct sum of G alpha with some obvious notation. Okay, and so this is equivalent to say that for any point S in S, the map from the map which sends, the map which sends alpha to alpha of S is bijection from R to the root system of, well, the usual root system of this. Okay, so well, and let me say first that so Conrad, so this is notes of the Lumini conference on SJ3. And define roots as constant elements of M. So so this is, I'm not sure how much this extra generality is needed. This is a generality chosen by de Mazure. Well, I think there are some good reasons for this, but so this is really some not some inessential point. But so let me just give an example to explain what's the difference between the two things. So let's just take a field which is algebraically closed and consider a base scheme which is disconnected. So this is two copies of the spectrum of K. So one just want to be nasty and consider a disconnected thing. And we consider G, well, the split group SL2 over S, and T, the maximal torus of diagonal matrices. And then G is T plus G alpha plus G minus alpha, where alpha is the usual character which sends a diagonal matrix like this to T square. Okay, so R equal alpha minus alpha. So this is a root system, a constant root system. And well, that's of course that's the natural one, but we may consider the morphism. Let's call it beta from T to GMS, which is alpha on S1 and minus alpha on S2. Then beta minus beta is also a root system for GT. Okay, so the picture, so we have those 2 points, and so at each point the weight space in the Lie algebra are alpha and minus alpha, and so the natural choice is to take the the constant choice is this, but somehow perversely or maybe for reasons of descent theory, it could be that one has chosen this pair of roots. So it's a very minor point, but one has to pay attention that these things can happen about above a non-connected base, and so there is this statement that if we fix a root system, then any root is locally on S an element of the root system, but it's only locally because you see if we take the constant root alpha, and then beta is neither alpha nor minus alpha, but locally it is, here it is alpha and there it is minus alpha. So, and I think this extra generality is needed for purposes of descent theory, because we start with the easy case where there is a split maximal torus, and then we do have roots which we may choose to be constant. But the next step of the game is we do not assume that T exists. So we will only know that after some metal extension, this is a situation. And we want, and so we will have things on the original base which are obtained by descent. And then it's not clear what we get. And so we have to allow for this more general things, but it's only a technical point. Okay. Okay, so for the moment, we can think as root as nice, honest, constant roots. Okay, so now we want to prove the first important results. Okay, so let me not erase this. Okay. Okay, so we have this, and let T be a split maximal torus of G, and let alpha be a root of a GT. And so the goal, we want to construct subgroups U alpha, U minus alpha in G. Okay, so well, we have the torus. Now we want to go to construct the root groups. And so, no, for any group, let yes, yeah. Having, well, yeah. Yes, so we work in the case where there exists a split maximal torus. And now for any root, we want to construct the corresponding root subgroups. And so the first step, as in the classical theory, so we look at the kernel of alpha, which is a subgroup of T, and we denote by G alpha the centralizer in G of this kernel. So this is closed, smooth subgroup of G, and with reductive fibers by the classical theory. And the Lie algebra of this group is the torus, and there are only these two root spaces. Okay, because fiber-wise, well, in a geometric fiber, we have a reductive group of an algebraic closed field, and by the classical theory, we know that the centralizer of this guy of an algebraically closed field is a reductive group of semi-simple rank 1, and it has only the two roots, alpha and minus alpha. Okay, and so we have, so this one is much smaller than G, and it will be easier to construct the root groups U alpha and U minus alpha in there. Okay. And we have the following theorem. So in my notes, it has this number. So firstly, there exists a unique group homomorphism. Let's call it exponential alpha from G alpha to G, which is normalized which is the equivariant. So this means, because the torus acts on G alpha by the adjoint action, so this means that only S prime over S and any T in T of S prime and X in G alpha of S prime. So this means that if we compute exponential of T acting on X, which by the definition of the action is just alpha of T times X. And so this is T exponential alpha X. Okay, so this group homomorphism intertwines the adjoint action on the Lie algebra and the action by conjugation in the group. And the claim is that there exists a unique such homomorphism, and it is, and moreover, it is an isomorphism from G alpha to a closed subgroup U alpha of G alpha. Okay, so this defines the, so in the process of this, we will see that there is an enclosed, which is smooth, of course. Okay, so the subgroup will be constructed in the process of proof. And of course, similarly for minus alpha, and so we obtain we obtain also a group corresponding to minus alpha. So this is the first assertion, which is the long one to prove. And then it's easy to see that the multiplication map induces an isomorphism and so the multiplication map is this multiplication map is an open immersion, and I call omega alpha its image because I will need this, and so this is an open subset of G alpha. Okay, so the hard part is to construct the group U alpha and the exponential isomorphism. And then once we have this, it will be easy to obtain the big cell. Okay, and yeah, so actually it is called the big cell in G alpha. Okay, and so the proof of this theorem will take some time, but let us start. Okay, so the next section is the so-called dynamical method. Dynamical method of Konrad Gabor Prasad. Okay, so before I explain what is this, So the original proof in SGA3 was the same method. So U alpha exists. We take some U alpha on some fiber. One uses a Hochschild cohomology argument to lift it to infinitesimal thickening of this point, then to the compression of the local ring. Then another trick to reduce to the ancialization of the local ring. And then we have U alpha. And then the existence of the exponential map. The proof is essentially the same as in what follows. One proves uniqueness first, that if it exists, it is completely unique. And so the existence can be proved et al. Locally. And et al. Locally, it works. Okay, so there is a proof in SGA3, but the dynamical method provides a shortcut. It gets very quickly the existence of U alpha. So let's go for this method. So let's start with a very easy example. But okay, so let's GM S acts linearly on the three-dimensional space by okay, so we consider this as a vector bundle. Okay, so let me call this V. And we call the standard basis, I call it E0, E1, E2. So the action is, well, T acts trivially on E0. T acts on E1 by multiplication by T. And T acts on E2 by T inverse. Okay, so the action on an arbitrary vector is just minus x2. Okay, so clearly we have here a line of fixed points. Okay, so fix. So this is the line spanned by E0. And let's call it V0, like fixed points. Let's call V plus. So those X in H3 such that the limit when T goes to 0 of Tx exists. And so we see that this is the span of E0 and E1. Okay. Because you cannot allow a non-zero third coordinate, because otherwise you could not extend this morphism to at the point 0 of the affine line. Okay, so the positive part is just the first two coordinates. And you know that if we take some x in this positive part, well, of course, the limit that you get, well, you get a fixed point. Okay, so you take this, so. And so you see that the positive points, so these are the points x1, x0, x1, 0. And any such goes, so if we make t act and then t tends to 0, so this goes to, okay, so the action is contracting this two-dimensional subspace to the line of fixed points. Okay, and we can define similarly V minus, which is a set of those x in such that the limits went of the inverse of x exists. And so you see that this time this is, okay, so this is the negative part. And, okay. And yes, well, actually, this is a very, I think this is a very old idea. What I'm going to say, so at least, well, it was used by Bialynicki, Birula in the 70s. Yes, sure. Yeah, sure. And yeah. So I think that the idea is that this works. We can make GM act on any variety instead of just a vector space or projective space, and it gives good results in a more general setting. So of course in this setting, so this is quite old. Well, it goes back to Hilbert actually. But I gave this example because I just one piece of notation, and so we say, following our three authors, that GM acts on so the coordinate ring of a affine space. Okay, so by T acting on Xi evaluated at a point X. So this is Xi of T of X. So I mentioned this because this was not my usual convention, and so I was confused. And so okay, so let us follow this convention because so with this convention we have that x0 is fixed and t of x1 is tx1 and t of x2 is t inverse x2. Okay, so usually if, for example, if you take G acts on V in the natural manner, so it's it acts on the ring of function, or let's say over a field. So the ring of function is a symmetric algebras of the dual vector space. And so it acts on a function by phi of G inverse. Okay. Okay, so in general, if you want a left action on the function, you have to put a G inverse here. And this is, okay. And if we were to do this, the signs would be reversed. Okay, so this one would have weight -1, and this one would have weight +1. But they chose this convention because probably they wanted to have only positive signs. And so I will follow this convention. Well, since GM is commutative, there is no problem. But, well, one should note that because otherwise one is confused by the signs in the. Okay, so the first basic observation is that this generalizes to a GM action on any variety. Well, on any affine variety. And so let me state the result. So we have the following lemma, which comes from the book. And this is lemma 2.1.4. Okay, and so let V be an affine S scheme with action of the multiplicative group. Then, firstly, the subfunctor V plus of V defined by Poynting S scheme S prime. We want the S prime points of V plus. So these are just those V in V of S prime. Just the morphism. So let's call it rho V. So which goes from GM S prime to V S prime, and so which sends any T to T acting on V. Okay, so if we fix a point V, we have a morphism like this. And we require that this morphism extends to a morphism. So it extends to a morphism okay, so this we want this to extend at 0, and then we will set that the value of this morphism at 0, or we call this limit as T tends to 0 of T acting on V. Okay, so this is we define this at the level of arbitrary points, and the statement that is represented by a closed subscheme of okay, so I will use the same letter, but the point is that it is a subscheme of V, and similarly, for the negative part, as I defined previously, and the invariance V0. And secondly, for any V in so the point, so let's call this V0. So this limit that we want to exist belongs. So this is an invariant point. Hence, we get a morphism. Let's call it limit at 0, which goes from the positive part to the invariance. Okay, so we are going to prove this, and it's very easy, in fact. Okay, so we will continue with the main theorem tomorrow. So let's just prove this this statement. Okay, so proof. So, well, as usual, we may assume that S is affine. So you say it's a spectrum of some ring lambda. And then V is a spectrum of some A or some lambda. And so the GM action makes A into a Z-graded algebra. And, but more precisely, the action is given by morphism of algebras. So let us call it delta, or delta sub A, which goes from A to A tensor over lambda with this, which is a comodule map. Okay, so this is a Hopf algebra which corresponds to the multiplicative group. And so to say that the GM acts on the scheme V, so it means that it acts by morphism of algebras, by automorphism of algebras on A. And so the action is given by a comodule map, which is in this case also a morphism of algebras. Okay, and for any lambda algebra R, and so if we set S prime equals spec of R, then any point V in V of S prime is okay. So a point is just a morphism of lambda algebras from A to R, which sends a function to, okay, so a point with value in R is just a morphism like this, and I denote it by f of v. And then what is rho v? Then so this morphism rho sub v that we want to consider is the following map. So we have A, which goes by the coaction map into A tensor this. So an element F is sent to a finite sum of some element Fn tensor Tn. And then we evaluate V, oops. And so this goes into R. And so this goes to the okay, so this is and so this morphism extends to A1 if and only if for any F, this thing above is in R. So we want non-negative power of T. And so this means that for any F, we must have Fn of V is equal to 0. Okay. And so what are those? But for any F, if we pick some F which is already in the graded part of degree n, then the coaction is just Fn tensor Tn. And so the condition is that for any n strictly negative, and for any F in an, Fn de V is equal to 0. And so this means that V is in the closed subscheme defined by the ideal generated by the negatively graded part. Okay, so this proves this. So okay, so V plus is a closed subscheme defined by the ideal generated by the negative part. And let me just finish with the statement that the limit is a fixed point, which is not difficult. So where can I write this? Okay, so let me erase the statement and just prove the last statement. Okay, so now if we take V, which is a positive point, then for any F in A, if we write delta of F is the sum of Fn tensor Tn, then and so what is this limit? So if I call V0 this limit, sends F to okay, so the condition for being in the positive part is that there are no negative powers. And then the limit, we just make t is equal to 0. So we just take the, so we just get this. Okay. And where f of the f0 is defined by this, and for any n in Z and any f in AN, we have the formula that f of v is equal to, sorry, f of v0. So this is f of v if n equal to 0, and this is 0 otherwise. Okay, and so this means that the map rho v0 of okay, so this means that for any, so this map takes any f here. So this is f evaluated at v tensor 1, because all the other terms vanish. And so there remain only the t to the power 0, which is 1. And so this means that V0 is invariant. Yeah. So this rho sub V0 of F Yeah, it's the same actually. Ah, uh, yeah, no, well, yes, you're right. It would be better to write f of zero is here. But so the point is that on the right hand side, this is one. Well, okay, I realize that I changed notation slightly because previously, well, so previously, so this was a function ascending t to something, but so this is the same thing. So this is a polynomial, and so this is obviously in function on GM. Okay, and so we have proved our theorem. And before we stop, just look at this beautiful example. What do we get if we take V to be SL2 and GM acts by conjugation? So I made the computation for you. So we take a matrix in SL2 and we conjugate by this diagonal torus. And we see that the diagonal terms are unchanged. And so this gets multiplied by T2 and this by T minus 2. And so we see that then the positive part is the Borel subgroup. And there is this evaluation map L0, which goes to the fixed point. And so this is the torus itself. And it turns out that, so this is acting in fact by automorphism. This preserves the group structure. And so this is a group homomorphism. And so we can consider the kernel. And the kernel is the subgroup of unipotent matrices in SL2. And we will see that this is exactly what happens in general. Okay, so this works in the generality where we add this G alpha, which is reductive of rank 1. So there is the torus. In the Lie algebra, there is just the torus and two root space. And the result is exactly the same. So the positive part is the Borel subgroup whose Lie algebra contains the G alpha. And the limit part goes into the torus. And the kernel is a closed subgroup we were looking for. Okay, so we will continue this tomorrow. But so this dynamical method, well, they called it dynamical because we take the limit as t tends to 0. And so this gives very quickly the existence of a closed subgroup whose Lie algebra is G alpha. Yes. Yeah, I'm going to use this tomorrow. So actually, the argument of Bialynicki-Berula is precisely that this U alpha is isomorphic to the tangent space at the identity. So there, well, by the action of T, we can, well, so we look at the tangent space, or rather the cotangent space, the identity, so which is m over m squared. And there is a natural map from the symmetric algebra to this, of this vector bundle into U alpha. And it is an isomorphism because it has to be so. And yeah, and so this is the end of the argument. Okay, And so tomorrow we will finish with the proof of the theorem. Okay.